Hello. In this video, we will introduce the formula for area between two curves like this, and then we do a couple of examples. So let me start by remind you which chapter and section this topic is in our textbook. It's in chapter 6. And the first section, chapter 6, is applications of integration. This is 6.1, area between two curves. Now, let's recall what we learned in our Calculus 1 class. So suppose we have a function f whose graph is above the x-axis. That means f of x is greater than 0 or equal to 0 for all x in the interval ab. So the function is above the x-axis. Now the area under the graph of this function, this area above the x-axis, we learned in Calculus 1, is that the integral, the definite integral from a to b of f of x dx. So that is the area under the function f. Now, considering our situation here, we have two functions. Let's suppose that these two functions are both above the x-axis. So to calculate the area between these two, what we can do is find the area under the graph of the function f using this formula, and then find the area under the function g. Okay, again using the same formula. So this is the integral of g of x dx from a to b. That gives us the area under the graph of g, and take the difference of these two integrals. So the first integral is the integral of f of x dx from a to b. That's the area under the graph of f up to the x-axis, all of this up to here. And this one is the area under the graph of g. So if you take the difference of these two, that will give you the area under the area between the two functions. So that's what we have here. The big area minus the small area gives us the area what we need. A short form of that is take the difference of f and g, and then take the integral. That's because the integral you can distribute that through the difference of two functions. Okay, well, what happens if I have two functions that are not completely above the x-axis? So I'm going to draw a couple of graphs, functions. So suppose this is your function f. It's not completely above the x-axis. Say this is your function g. Maybe, or part of it, maybe not above the x-axis. And we're looking from point A to point B to find the area. What we can do to find this area is we can implement this idea if we shift the graphs up above the x-axis. So find a big number k and shift it by k up above the x-axis. So you look at f of x plus k for one of the functions, and g of x plus k for the other function, shifting them up, and then take the difference and get the integral, which will give you the same formula like that. So in all cases, the area between the two is the integral of f of x minus g of x dx from a to b. In short, I look at it as the area of the integral of the top function minus the bottom function from a to b. And that's how we calculate the area. Okay, let's just have one example, and then we will expand this idea a little bit. Okay, now I have two functions, y equals x and y equals x squared, and we want to find the area between these two functions. Now you notice that there is no a and b given in this problem. The reason being that the two functions do intersect at two different points, at least 2 points, and make a region like so. Okay, so to do, before we do the integral, the first step we have to do is always set the two functions equal and figure out where the intersection or intersections are, where the intersection is or the intersections are, because the functions may intersect. Okay, you may have a situation like this where they may intersect at 1 point or at 2 points or maybe more. Okay, always before you start doing anything like this, set the two equal and solve. In this case, I have x equals x squared. The function f of x, one of them is x, one of them is x squared. Okay, set the two equal. This gives you x minus x squared equals 0. Factor x, so we have 1 minus x times x equals 0. So this gives you x equals 0 or 1 minus x equals 0. Okay, which gives you that x equals 0 or x equals 1. So we have two intersection points. One of them is when x is 0. You can stick that to one of these two functions. It doesn't matter which one. Okay, stick 0 in. The y value is 0. So that's the intersection point, 0, comma 0. And the second intersection point is when x equals 1. Stick this into the function, one of the two, doesn't matter which one, because they are equal at that point. So when you stick 1 in, 1 squared is 1. So they intersect at 1, 1. And that's the second intersection point, 1, comma 1. And now we know these two functions, y equals x and y equals x squared. We can draw the graphs of these two functions. But if we didn't, there's one thing we can do. So between x equals 0 and x equals 1, which one is the top function? To find that out, what we can do is we can plug a sample point, a test point, I should say x equals 1/2 maybe, and stick it into the two functions and figure out which one gives you the larger functional value. So if you stick 1/2 in for x, you get 1/2. On the other hand, if you stick 1/2 in for x in this one, 1/2 squared is 1/4, which is smaller. So the top function should be this one, and this is the bottom function, even if we don't know how to draw the graph of the functions. Okay, it just works out well like that. Now, for the area, we will be integrating from x equals 1 to x equals, from x equals 0 to x equals 1, from this point to this point. Those will be our a and b. The top function is y equals x, the bottom function is y equals x squared, like we saw earlier. Okay? So the area is the integral from 0 to 1 of the top function minus the bottom function, which is x squared over 2 minus x cubed over 3. That's the integral of x is x squared over 2. Integral of x squared is x cubed over 3. We'll evaluate that from 0 to 1, which gives us 1 squared over 2 minus 1 cubed over 3 minus 0 squared over 2 minus 0 cubed over 3. That's your f of b minus f of a. This gives you just 1/2 minus 1/3 minus 0. And this gives you, I think, 1/6. Its common denominator is 6. 3 minus 1 is 2. 3 minus 2. This gives you 1/6. And that's the area of our region right between these two right here. Okay? All right, let's do a second example. I have the area. We want to find the area bounded by y equals 9x and y equals x cubed. So like what I said earlier, we're going to set the two equal. And solve. Okay, so this gives you 9x minus x cubed equals 0. Okay, or just move the 9x over. So x cubed minus 9x equals 0. If you factor x, you get x squared minus 9 equals 0. X squared minus 9 also factors. That factors as x minus 3 times x plus 3. This says that x equals 0, or x equals 3, or x equals negative 3. So these functions intersect in 3 different points: at 0, at 3, and at negative 3. So if I want to draw the graph of these functions, let me see if I can make a line. Okay, that's your x-axis. Then they intersect at negative 3 and at 0 at x equals 3. So if you look at if you calculate the y components, negative 3, and you stick negative 3 into x in one of these two, either one, will give you negative 27. When you stick 0 in, it gives you 0. When you stick 3 in, you get 27. So at negative 3, I'm just going to call this as kind of randomly as negative 27. And that will be my 27. So that's one intersection point, one intersection point, one intersection point. I don't have enough room to scale it that way, so I'm just simply picking 2 points equidistant from 0. Now, y equals 9x is a linear function. So that should be y equals 9x. And y equals x cubed goes like so. It's flat at 0 and goes back up. So we know it goes through the point 3, 27 because we did the calculation. Now, in this situation, which one is the top function and which one is the bottom function? Well, partly the x cubed is a top function, and partly the 9x is the top function. So to calculate the area, we need to do 2 separate integrals. Okay? Integrate from negative 3 to 0 for this area of the top function being x cubed minus the bottom function being 9x dx, plus the second integral from 0 to 3, this guy here, of the top function being 9x minus the bottom function being x cubed dx. Okay, so we have to do 2 separate integrals. We can look at this function, this particular area, region, as symmetrical and calculate one area and multiply by 2. That is possible, but that's very rare situation. So I'll just do it simply following my nose. I'll calculate the area of this piece, which is this guy, and the area of this piece, which is this guy. Okay? And then add the 2. So that equals x to the 4th over 4 minus 9x squared over 2 evaluated from negative 3 to 0 plus 9x squared over 2 minus x to the fourth over 4 evaluated from 0 to 3. Okay, I'll try to be careful here. Stick 0 in will give me 0 minus negative 3 over 4 to the fourth is 81. Negative 3 squared is 9, so it gives you 81 over 2. Plus, stick 3, this gives you 81 over 2, minus stick 3 for the x to the fourth, 3 to the fourth is 81, minus 0. So that's the second integral, this is the first integral. Okay? So you notice that this is half of that. So when you take the difference, you get negative 81 over 4. Plus, and this is exactly half of that. So when you take the difference, you get 81 over 4. So this is minus minus gives you 81 over 4. Plus 81 over 4 gives you 81 over 2 as your final answer. Okay, so when we have a situation like this, when one function is not clearly on top, one function not clearly in the bottom, they just cross in between, then you have to separate the integrals and add each area. Okay, so in general, first thing you need to do is set the two equal. Then separate and solve. Okay, so once you get the intervals, say they intersect at maybe 2 places. So your point A and point B might be here. Say they intersect in 2 places. I'm just going to make 2 functions. I'm getting myself in trouble. I should have first drawn the graphs of these 2. Okay, this may be y equals f of x. And this may be y equals g of x. So when you set the 2, you're going to get C and D. And you could take test points to figure out which one is the top, which one is the bottom. Okay. Once you do figure out which one is the top function minus and which one is the bottom function, then the area is really the integral from a to b of the top minus the bottom. But in this particular case, you're going to do from a to c of f minus g plus from c to d of g minus f plus integral from d to b of f minus g. Well, there is a shorthand for this. The actual formula, which is really, we don't reuse it in calculations, is the area is the integral from a to b of the absolute value of f of x minus g of x dx. That's actually what we are doing when computing this integral. So that's actually the formula, but I didn't state it early simply because this is not a working formula. Okay, the working formula is really to set the 2 functions equal, find out where they intersect, find out the integrals of each piece, and when you get negative integral, really means that we have the top and the bottom mixed up. So we find out which one is the top, which one is the bottom in each subsection, integrate each subsection separately, and add. And that's the working way of computing this weird integral of an absolute value. Okay, so that's exactly what I did in this example. So they gave us 2 functions, y equals 9x and y equals x cubed. We didn't know which is top, which is bottom function. We set it to equal, solved it. Okay, for graphing purposes, we found the y components. So we did do the graph after finding the y components. Then in each section, we could do test points to figure out which one is the top, which one is the bottom. Okay, in each section. So compute the integral of each section separately. Once you get an answer for the first one, an answer for the second one, add the two. That will give you the final answer. Okay, this we will have a few more examples like this in class tomorrow. And have a wonderful day. And I'll see you tomorrow.